Very happy to have Tristan Tomala from HEC Paris to talk about linking mechanism with few messages. Tristan, the floor is yours. You have 1 hour, 30 minutes. So go ahead.
Okay, so thank you. Thank you for being here. Thank you for having me. This is a joint work with my colleague Maël Trust, who is a computer scientist. He works in France and is a specialist of information theory. So what we do here is work on the interface between game or economic theory and information theory. So this is a broad project which is about strategic transmission of information between sender and receiver, but with information constraints which are not necessarily always modeled in economic models or in game theory models, but which are super common in information theory. Okay, so oops, I will go directly to the model to explain the problem. So here is the communication model that we have. So it's a two-player problem. There is a sender and a receiver. So the students who attend the course, we just talked about sender and receiver this morning. Now, the sender observes states, but not only one state, but a sequence of states. So there is an IID sequence of states. So it's written Sn, and it's drawn from a finite set from a fixed a priori full support distribution. Okay? So this is drawn by nature, let's say, and this sequence is known by the sender. Then the sender has to choose a message in a set, in a finite set. And then the receiver observes the message, and from that message is going to choose a sequence of actions. Okay? And at the end, when the actions are chosen, each player is going to receive an average payoff. So this average here, the average of the U of ST80, that's the average payoff of the sender, and there is the average payoff of the receiver. Okay? So there are two comments to be said about that. So it's not exactly a simple one-shot communication problem, because you don't have just one state variable, but you have an IID sequence of state. But it's not a repeated game either. It's not a repeated game either, because a repeated game, there would be stages, and at stage T, you would learn state ST, and you would take action AT. Here, before, at the first step of the game, the sender observes the full sequence. And then the receiver gets some information materialized by the message, and then chooses a full action sequence. And then there are average payoff which are materialized. Okay? So that's one element of the model. Another element of the model is this message space. It is usual in economic and game theory, when you talk about mechanism design or information design or communication equilibria and stuff like that, to allow for arbitrary message spaces. And in particular, in general, you would take a message space that would be large enough so that all information that you need to convey is expressible within the message space, but here it's not the case. Here, you see the message space M has some cardinality, and you see, depending on the parameters R which is there, it could be smaller than the cardinality of S to the power N. So think of this message space as some binary string of some length, like the pair 0, 1 to some power. Yes? Think of this. So think of as a number of bits of information, of binary bits of information that you can transmit. Okay? So perhaps due to the parameter R, which is a restriction, you don't have enough bit of information to faithfully report what would be the sequence of states. Okay? So R, the number R, if you calculate, that's just 1/n times the base 2 logarithm of the cardinality of M. And again, think of M would be a binary string, so that would be the pair 0, 1 to some power, right? That would exactly be measured by this, right? Okay? So R, it's a very common measure in information theory, and it's called the rate of transmission. Because if you think of it, N is the number of stuff you need to communicate about, and this number R is the number of bits, of binary bits of information that you can transmit per unit problem. Okay? So that's the rate of transmission. Okay. And then, okay, there are strategies for the sender and for the receiver. All right. Oh, yeah, that's what I wanted to say. So this project, it's an unfinished project. I will show you some result, the partial result that we have, but we are working on that since a long time, and we still have many, many open questions. In the title, I wrote linking mechanism. I will give the reference later on. It is linked to an econ paper of Jackson and Sunshine. This is Econometrica 2007, where they consider a very, very similar model where you have many decision problems that are independent of each other, but you have to treat at the same time. And instead of treating one problem at a time, you might be better off in linking the problems together. I will explain what is their result and how this is useful for us. In the paper, Jackson and Sunshine, they motivate that by voting problems where you have to vote on several issues at the same time. And you know, and Rida knows this much better than I do, that there are models of storable votes, and you can have budget for voting, and you allocate your budget to one problem versus another, and so on and so forth. So there are models like that. But in information theory, what they have in mind, if you want to have a motivation, would be image reconstruction. So think of ST being bits. So you have an image, and you have colors, so they can be black or white, right? So the image is a long, very, very long sequence SN, right? N of bits, let's say black or white, or maybe red and blue, and so on and so forth. And at the end, you want to reconstruct the image. But then there are algorithms of compression, right? And that's because, and here there is some economic insight there, because you cannot and you don't want to transmit all the image. You definitely want to compress it to save on bandwidth, to save on time, and so on and so forth. So that is the question of that is the problem of information theory, to have some optimal rate of compression, right? So here we're going to treat this as a constraint. You need to compress within this rate of transmission. All right? Now, so in this model, which is a little bit in between information theory and economic theory, there are features which are strange to economists. There are features which are strange to computer scientists. So one feature that might look strange to computer scientists, but not that much, is that the payoff function of the sender and of the receiver are not the same. Well, it does happen. And in particular, later on in this talk, I'm going to talk about the receiver having commitment power. That is, we're going to know what is the strategy of the receiver, and sender is going to take a best response to that. Okay? So this has some implication. I mean, this has some bite also in computer science and in image reconstruction, because think of this. So here we are going to think of the different utilities as they are both strategic and they don't want the same. But in this theory of reconstruction of images, videos, or whatever, you could say, well, there is an algorithm, the receiver, who decodes in a certain way, and maybe that's not the way you want it to decode, and then you need to adapt to that. So they have problems which are extremely similar to that, where the objective of the sender, i.e. the encoder, is not aligned to the objective of the receiver, i.e. the decoder. So for instance, that's not my expertise, that's what my colleague told me, JPEG or MP3, they are just fixed algorithm for decompression. So if you're working with JPEG, this means that this strategy is fixed, and you optimize given this strategy, which is one decoding algorithm. Okay, I don't pretend to know what I'm talking about there. Okay, but still, I think this is some good motivation. All right.
Excuse me.
Yes.
Transmission can be less than 1.
What's that?
Rate of transmission can be less than 1.
Yes. For instance, you could say that. Imagine that you have 4 states, like the cardinality of S is 4, and you have just 2 messages. So basically, you just transmit 1/2 bit per unit of time, if that is not exactly time, but you see what I mean.
Typically, it should be less than 1, right? Or
Not necessarily. It's not just necessarily comparable to 1, but I'm going to relate that to the entropy of the source, namely of the entropy of the prior. No, this is a constraint, right? This is a constraint. So if your rate is high enough with respect to the cardinality of S, you're fine. The problem is when R is small with respect to the cardinality of S. That's the problem.
So we need to compare R with cardinality of S.
That's right. That's right. I will give you a condition. You will see it. Yeah. All right. Okay, so since we are interested in empirical payoff, we are going to be interested in the induced empirical distribution of states and action. So this is the empirical distribution of states and action. Okay, so this is the realized empirical distribution, and this is the expected empirical distribution. So so I can just remark that the expected empirical distribution over states is just the prior, because states are IID. So we are going, yeah, okay. I will get to the conditional in a moment. But the question is going to be, can we characterize the achievable or implementable such distributions given the communication restriction and given the incentives of the player? Okay, so there will be constraints on the set of possible distribution. Some constraints will come from the information restrictions, and some constraints will come from the incentive of the players. So we're going to see that. Okay, so a first constraint is that, so I think of this as a physical.
Could you come back with the definition, please?
Yes.
Can you tell here just dimensions? S and 8 is one-dimensional? So
Yes, this is one-dimensional. This animal here,
what is sigma and tau?
sigma and tau are the strategies, right? Sigma, recall, this is a strategy that maps Sn to delta of m. And recall that m depends on n. And tau takes m and chooses randomly an action sequence. Okay? So sigma and tau, together with the prior, with the IID prior, they fully describe the probability distribution over everything, right? And then you calculate what is the expected occupation measure, if you will, of states and action. Okay? And this animal here now is a one-stage distribution between states and actions. Okay? So that's in, right?
And
Pi is the prior. Pi is the prior, and you calculate just this is the marginal of this guy over states. So this is this expectation, but states are IID with respect to pi, so that's pi. Right? Okay, so what I want to show you is a bunch of constraints coming from various reasonings that the implementable distribution need to satisfy. So first is a physical constraint, if you want, is that the mutual information between the random state and the random action cannot be more than the rate. Okay, so let me comment on that a little bit more. So what's the mutual information? Mutual information is one measure of correlation between two variables. Okay, it is zero only when they're independent, and otherwise, if it's positive, it shows that they are correlated. So what is that? If you have seen it before, you know what I'm talking about. If you've never seen it before, you can see that this is the Kullback distance between the joint distribution and the product of its marginals. But it is also the difference between the Shannon's entropy of the states minus Shannon's entropy of the states conditional on the action. So there is a literature in economics on rational inattention which uses this as a measure, and they call that the entropy reduction. Okay? They call this the entropy reduction, namely the initial uncertainty that you have over the state is measured by the entropy function here. Now you get to observe the action, you have less uncertainty, so the difference is a remainder uncertainty. And you call that the mutual information, and okay, right? So now I can go to answering Alexei's question about the relationship between R and the cardinality of S. The entropy of S cannot be more. The entropy of S must be less or equal to the log of the cardinality of S. Always, right? Because the entropy of S is maximized with the uniform distribution, and the entropy of the uniform distribution is the log of the cardinality of S. So when R is greater than the log of the cardinality of S, this constraint is always satisfied, it has no bite. Okay, so it would be interesting, indeed, when R is less than either this or that, either less than the log of the cardinality or the entropy of S. Otherwise, it's not important, it's not interesting.
Can you repeat what's the name for that? It's a distance? You call that distance?
Yes, this thing. So it's a Kullback distance. Sometimes it's called Kullback-Leibler, right? And it has an expression such as this. Okay, so this is the expression of the Kullback distance. So sometimes it's called KL for Kullback-Leibler. This is not exactly a distance because it's not symmetric. It is zero only when P equals Q. And yeah.
It's basically how different the product of marginals with the true distribution.
That's right. That's right.
Here it's symmetric because the way it's written it looks symmetric, but if you measure the distance between P and Q, P, S times Q,
This is not symmetric here in this expression between P and Q. I mean, it looks symmetric between these two terms. And in fact, the symmetry is reflected here. This is equal to this. So that's the symmetry that it satisfies. But now if you take this distance between P and Q, this is not a symmetric. This is not exactly a distance. Right? Okay, but then whatever be the strategy, this information, this measure of correlation at the empirical distribution we're interested in cannot be more than this constant R. So this is the restriction. So basically, just to give you an idea, this is going to, this triangle is supposed to represent some set of probability distribution, right? And the set of probability distribution that verify a constraint like that, this is going to look something like this. Okay, because you have logs somewhere, so this is going to look curvy. So it can have flat parts a little bit. It is smooth. It is not exactly a circle. It looks somehow like this produces constraint that looks somehow like that. But in general, this is convex. This is a good convex set of. Okay. Here is the proof, but probably I want to skip it in the interest of time. I think, yes. There are two elements to the proof. One is that these three variables have the Markov property, right? Namely, there is a probability, transition probability from Sn to M, and there is a transition probability from M to An. So I can say that this triple of the sequence of three random variables has the Markov property. When you have the Markov property, the mutual information between the two endpoints is less or equal to the mutual information of 2 points in intermediary. And intuitively, M is a sufficient, no. I mean, you can phrase this in terms of sufficient statistic, and I'm going to screw it if I try, but you know more about Sn when you observe M than when you observe An, okay? And you can phrase this in terms of this being a sufficient statistic of the other. And again, I'm going to say it the wrong way if I try. OK, so that's one. And the other one is that there is a Jensen inequality somewhere because all those things, they have the right convexity property the way you want to have them. All right? So you can believe me on that. That's not very difficult. And again, this is a physical constraint. All right, so let me skip this. So now, we are going to, OK, so now I know that I can restrict my attention to distributions which satisfy this constraint, plus that the marginal distribution of a state is pi. OK, now I want to add incentive constraint to the picture. Okay. OK, so here is the first benchmark. Non-strategic player, full cooperation. So if you want common payoffs, so they have common interests, so they cooperate, they agree to cooperate. And then this is a theorem. It is due to Shannon, an old theorem of coding of Shannon, but it's also related to a more recent result by some other information theorists in 2010, because Shannon was not exactly formulating things in terms of average distribution. He was just interested into reconstructing a sequence, not necessarily on average. So this 2010 paper makes it more precise on average. But the idea is that basically the two conditions that I've shown you, they are sufficient. So if you take a distribution that satisfies this, if you take an epsilon, and if you let n be large enough, then you can find an encoding strategy sigma, a decoding strategy tau, that is going to yield something which is approximately your target. Okay, so basically, the idea is that these two conditions, they are necessarily insufficient. Okay. All right. One comment, perhaps, about the method. There is a very powerful method which has been invented by Shannon and which is actually used in econ papers without them really realizing that it has been recognized by Shannon before in information theory. But the idea is the following. If you have an IID sequence in a finite set, with very, very high probability, the empirical distribution of the sequence is going to be close to the prior. Can you believe that? If you have an IID sequence of zeros and one, let's say 1/2, then if you look at the empirical distribution of a sequence, namely what's the average number of ones in your sequence, then it's going to be very, very close to 1/2. Okay? That looks just like the law of large numbers, but if you can make it a little bit more precise, you can say this. You can say that you have a very, very large set of sequences that have approximately the right distribution. So that's exactly, in fact, what Jackson and Sonnenschein called the quota mechanism. So what they do, they have a principal who observes an agent. The agent reports sequences of types, and the principal says, okay, what is your sequence of types? If it looks about right, I'm going to accept it. If it looks wrong, like if the empirical distribution is too far away from what I expect, I'm going to refuse it. And when I do that, I'm going to change it into the closest acceptable sequence. Okay? So that's what Jackson and Sonnenschein do, and that's more or less what Shannon was doing. More or less. More or less because information theories, they don't care about incentives, so they just say, oh, I get a random sequence, bad luck, I throw it to the trash. Okay? And that's not exactly what is done in the mechanism design paper. Okay. Okay. So now I will have the following model. At least in this paper, we study this model where the receiver chooses its strategy beforehand with commitment. That is, tau is announced, fixed once and for all. Okay? So in terms of computer science, you say, my decoding algorithm is JPEG, and that's what it is. It's nothing, it's not anything else. In terms of economics, you say, receiver is the principal, and the principal commits on how it is going to map messages into sequences of actions. Okay? So now we have, in terms of economics, a principal agent problem somehow, or a mechanism design problem, where the principal need to choose tau, but what we want to analyze now is the best response of the agent, namely the best response of the first player. All right? Okay. So what we are going to study, what I will try to show you, is what are the distributions that can be achieved under this condition that the strategy of the sender is the best reply to the commitment of the receiver. And this is just the best reply condition the way you know it, is that given sequence of state Sm, I choose M with positive probability only when M maximizes this expected payoff. And for the student of this morning, this is exactly the condition, the best reply condition that we had for the sender. Given my information, I send message M with positive probability only if choosing message M gives me the highest payoff among all possible messages. All right, this is the exact same condition that we have studied with n equal 1 in the problem of this morning. Okay. Okay, so here is the Jackson and Sonnenschein condition. If n was 1, if there was just one problem, and if you're used to mechanism design and principal agent, you would expect the following. You would expect that the commitment of the principal incentivizes truth-telling by the agent. Namely, you would expect that if I know state S, I get a better payoff by reporting S than reporting S prime. Yes? But here, with the logic of Jackson and Sonnenschein that I told you about, the principal is not reported a sequence, a single state is reported a sequence. So he can say, well, okay, either the sequence looks right, I accept it, or if it doesn't look right, and then I change it to something else. Okay? So what does that imply? This implies that you can relax the incentive condition on the agent. Again, that's the work of Jackson and Sonnenschein to do that, to say now, the only deviation that I need to deter from the agent are the ones that I cannot understand or cannot detect. And I cannot detect whatever deviation there is that preserves the marginal distribution. Namely, there are zeros and ones equally probable, 1/2, 1/2. If you change, if you swap all the zeros and all the ones, I cannot tell the difference. Okay? Both sequences, they look good on the face of the empirical distribution, but I cannot tell the difference. So this is the condition here. If you have a reporting strategy that in state S reports state S prime with the properties that the marginal distribution of the reported state equal to the prior distribution, then this row here materializes one deviation that I cannot detect, and therefore it must not be profitable. That's the Jackson and Sonnenschein condition. This describes a convex set of distribution. This is a bunch of linear constraints, and they are wider than just the one-shot, the single problem deviation. Incentive constraint, sorry. All right. So this condition is necessary. This condition is necessary. Any distribution that any distribution that I can induce with a best response of the sender must satisfy this Jackson and Sonnenschein condition. Oh, yeah, sorry, I went fast over that. D is whatever you can get with some strategy for some n. Okay, whatever you can get with some strategy for some n. Call that D. All right? For some n or for large n, here is more or less the same.
You should have put here the NR of tau.
No, because here you put all the sigma and all the possible sigma and tau. This is all the distribution for all the tau and all sigma, which is best replied to tau.
To some tau.
Some tau.
To some tau.
Yes.
It's not necessary. There is a, because here, as if
If you want, you can make this. You can spell this out and make this the union about tau, if you want.
I understand. So now you let also tau vary.
Yes, yes, of course.
You look
Of course. Exactly. Implementable means that for some n, the principal is able to find some strategy tau, and there will be some best response of the sender such that in the end you're going to implement that. Okay. So that's yeah.
Should be reconciled with the best reply of the receiver. It's just, I send an image, I need to receive another image. Otherwise, if I receive another image which is far from the first one, I'm losing something here. The example of images.
Yeah, it's not a perfect example, right?
No.
It's not a perfect example.
They have the same interest. They send an image,
And you receive the
and
same
you
image.
what you receive is something which is action space is the same as the strategy space, A equal S, and you want somehow to say that yes, this is this, this is this, this is this. So
Yeah.
one-
So there is that, but there is another thing which you point out and which is right and which is somehow a defect of the information theory model. But you're right first that you have in mind the idea that they have the same interest, so they want the image, the final image to be equal to the initial image. Now, if the image was completely random, like one half, you put black or white, it's completely unreadable, right? And you need all the capacity to be able to transmit it. So what is the force of the coding algorithm of information theory is to detect that here there is a lot of blacks, here there is a lot of white, so they play a lot with the correlation within the sequence that they want to transmit. So why this model imperfect? It's because the IID does not make sense in reality. So what I'm saying to your question is that you will be able to transmit correctly an image with a capacity smaller than the full capacity only when there is sufficient correlation. So that you know there is black here, so there must be black a lot around it. Okay, so the coding algorithm plays a lot with that. Okay, so but
in the case,
just to say that in this theory, they are aware that this theory has some imperfection in the sense that they consider mostly the IID case, but in reality, it's not IID when you make image reconstruction. But the IID case is sort of a worst case analysis. So you know that with the rate R, you will not be able to transmit something which has a mutual information greater than R. So this will be a constraint. And in reality, when you do encode really an image, when you use the algorithm, the less information there is in the actual image, the better, the easiest it is to transmit. I don't know if I'm answering the question. Okay, sure. Yeah. Okay. Okay. So we use this constraint, and we say, okay, this constraint is necessary because if it was not, then of course you would not have a best response of the sender, because if you contradict this means that the sender is able to choose a way to swap the states. Nobody can tell the difference. He's going to gain from that. So of course it was not a best response. So it is necessary. So now.
Sorry, just to remind, F is a set of feasible. GS is a satisfies condition.
So you have a lot of constraints here. This guy here indicates that the distribution you're looking at, the marginal of a state must be the prior. This guy indicates that the mutual information must be less or equal to R. And now this guy indicates that you have this condition on top of that. Okay, so I am adding constraint. Each time I'm keeping a nice convex set.
And we know that dr is convex.
Yes. We know that dr is convex. I mean, without any characterization and so on and so forth. I think we can show it. The reason is the following. The set Dn, when you fix M, they are compact. I don't think they are convex necessarily, but they are compact. And the sequence is not exactly increasing, but it is subadditive. Like D2n is greater than Dn. Dkn is greater than Dn. So it's like a somewhat increasing sequence with some fluctuations around some trend, right? And with this property, you can show that this sequence converges not exactly monotonically to the union, and you can show that the union is convex. But you need to work a little bit to make some approximation, but in the end, yes.
Like in repeat game.
Yeah, it's the same property as the union of the equilibrium payoff set of n-stage repeated game. It's also not exactly increasing, but it has this property of submonotonicity, and the limit is necessarily convex. That's exactly the same property. Yes. Okay. So now, we are going to introduce another ingredient.
One more question, but is it clear that there are some points in the feasible and based on Sonnenschein set that is not implementable?
I mean, given that they satisfy the capacity constraint as well,
Capacity constraint.
I don't know. That's where this work is not finished, and that's the main question that remains to be asked. Okay. So I'm going to make a picture to explain what happens here. So here I have the sender.
Sorry, why it's important?
Sorry?
Sorry, why this important? Why you just cannot work with the set F and G? Oh, you don't know whether it is. Okay, good. No, I took the question back. That's an important question. Good. Very good.
So I know that this is a necessary condition. Now I would like to know whether it's sufficient. Okay? So answer, I don't know. I have many examples and many particular cases where it is sufficient. I have an example which suggests that it is not sufficient. I will show it to you at the end. But now I'm going to enrich the model a little bit to make it sufficient. So there is the sender who knows the state, the sequence of state. There is the receiver. The receiver receives a message, and from the message chooses the action sequence. Yes? And now there is the message M here. So in the baseline model that I showed you, the sender chooses SN, knows SN and chooses the message directly. That part and finding out what's the best response way of mapping SN into M is very delicate, and we don't know exactly how to treat it. So I'm going to add another agent or player, which I call the encoder. And what the sender does is to say, oh, please, encoder, here is my sequence of states. Please calculate my message for me. Okay? So this agent, encoder, is not strategic, doesn't have any interest. It has some algorithm. It does whatever you want it to do. Okay? And then you just, so imagine of the, you have companies that do a lot of computational stuff in your stead. Like you have bid shading algorithm. If you want to bid in auctions, you have companies that provide you with how to bid because you don't know, you know your values, but you don't know how to bid, so you ask an algorithm to do this. What's that? Yeah, you have ChatGPT, you have whatever. So here I introduce this agent, encoder, and the encoder is able to collect a reported sequence from the sender and to encode it into a message. Okay? And here there is some strategy. Let me call that mu. And now the only incentive constraint for the sender is going to be to truthfully report the sequence to the encoder. So for the economist, this is more or less the mediator. This is what a mediator would do, right? A mediator in the sense of Meyerson. A mediator would come to the agent and say, tell me your information, and I'm going to choose your action in your stead. Okay? So that's exactly the idea here. So we know that adding a mediator to such game can only expand the set of equilibrium outcomes, right? So what is important to show is that adding the mediator cannot bypass the constraints which are here. So that's the lemma here. With a mediator, you can do a little bit more, right? But still, all the constraints that I've shown you, they are necessary even with a mediator. First, the mediator is in front of the message. It cannot bypass the capacity constraint. So that's explained that you still have the R constraint. And the sender can still lie to the mediator, so you still have the incentive constraint. Okay? So we have enlarged this a little bit, but we remain with this set of necessary constraints. But then, now this is sufficient.
Can you come back? Sorry. Can you explain? I think it's clear if an encoder just passes all the messages, then it's basically DNR as before. So how it enlarges the set? Can you maybe explain why adding an encoder will make it strictly larger? The set.
Well, because the encode, it's a little bit like why a communication equilibrium, why adding a communication mediator enlarges the, so the encoder can do randomization that you would not be okay with doing. Okay, so for instance, imagine that message M or message M prime, and now your expected payoff with M is larger than with message M prime, right? But then the encoder is going to randomize, let's say, 3/4 this, 1/4 that. If you have Sn, and if you have S prime n, is going to do 1/4 this, 3/4 that. Okay? So suppose that Sn prefers this, S prime n prefers that. Let's say. Yes? This system is incentive compatible. If you have the mediator, if you tell it Sn is going to do this randomization, you prefer this randomization to that randomization because you prefer M. And vice versa. But if you were to do the randomization yourself, you would lie. You would always randomize on M here and always randomize on M prime there. So the encoder or mediator can implement in an incentive compatible way some randomization that you would not want to do. Your agent would not want to do. Am I making sense?
I'm still not convinced why I cannot come up with some other mixed strategy equilibrium where I really want to randomize as an encoder does. Why the relation principle doesn't hold?
Again, so it does.
It does.
It does.
So it means
It does.
directly
Again, think that this gives a utility to Sn, which is 1, and the utility of Sn of M prime is 0. Okay? In M implies whatever the receiver is going to do. This gives some action, okay? And this gives you, at the end, something, your payoff is 1, here your payoff is 0. All right? And vice versa here. So now, if you're to choose yourself M or M prime, you're not going to mix. You're not indifferent. All right? But then the mediator tells you, if you tell me Sn, I'm going to choose M with a higher probability. If you tell me S prime, I'm going to choose M prime with a higher probability.
Let's imagine mu. Imagine that whatever you do, mu is random. Completely random. So meaning that sigma is always the best reply to something random, because if mu doesn't listen to what you do, just chooses random m, you add these options, I guess.
No, but But think of this in this way. You have
it's like a commitment device. Right?
exactly. You give some form of commitment. Imagine that you have finitely many messages, and this gives you finitely outcomes like this. All right? So now you're not indifferent between those. You're not indifferent, okay? So if you're never indifferent, whatever be your type, you're going to pick one of those points, but you're never going to randomize. But now, adding the encoder or mediator, you enlarge this finite set of points to all the randomization. So now perhaps this is your utility function, goes this way. So you strictly prefer, let's say, this randomization to that randomization.
And you basically can kill some of the strategies, right? So you have 5 possible strategies, but with encoding device, you can commit playing only between 2.
For instance.
Even if the third is attractive for some reasons to use.
Exactly. For instance. Yes, indeed. 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 Okay, so I'm going to conclude. So this is the best result that we have so far, which is that in this communication model with a mediator, we have the equality. We can achieve all those points. And now remains the Alexei's questions, which is the important one. Without the mediator, is there a gap? We think there is. And I don't know if I have time to show you all this.
Can you come back?
Stop.
Yeah.
Can you show that's our extreme point? Because you have a convex set, Our extreme point of FPR intersection of GS are in DR.
Extreme point, there might be a lot of them because
Yeah, you have a continuum of extreme points.
the R set, the FR set is like round here, okay? And the GS, well, it depends, it could be like this, right? In the construction, you don't go for the extreme points. The reason is that when you do the construction, you want some constraint, or at least many constraints, to be satisfied strictly. So instead, you don't want to try to implement this point or that point. You prefer to be there because you want to have strictness in many, many constraints. That helps a lot because you have all these epsilon and so on and so forth. So if you're on a knife edge case, bad things might happen in the construction. You need something more robust, so you prefer to be in the interior.
But when you have extreme points, maybe you don't need mediator.
I don't know. I don't know that. Perhaps. I don't know. I doubt it.
Mediator somehow is convexifying, you know. Maybe you don't need. No, it's not true.
I think it's more complicated.
You can prove that it's convex.
I think it's more complicated than that because it's not just convexifying a non-convex set. There are points potentially which are outside of the convex hull of what you can do without the mediator.
It's true what I said because dr is convex. So if all extreme points here are in the set, then dr will be equal to this the set you want to prove it to be equal to.
Yeah.
So it's implied that if you have a counterexample, you can prove it to some extreme points here which will not be
I guess so. So I want to end with a picture. I just want to show you a picture.
Can I ask you, so FPR is just your condition on E and R, right? It's a set of feasibility, right?
Yes.
And in JS, can you show JS condition one more time?
Here is GS.
Sorry about that.
So the R constraint, they're going to look smooth like this. And the GR constraint, they are going to be linear constraint on that.
But V is not here. It's only utility, right?
That's right. I did not yet try to maximize the expected principal payoff. Not yet. I'm just looking at what are the distributions that can be implemented given the incentive of the sender. And the ultimate step would be to choose the one that maximizes expected payoff of the receiver. And that, for now, I did not do.
But these all sets are given you, right?
Yes, V has no byte here. Because there is commitment on the receiver, so V is not really important. V is important at the end, at the last step. You characterize some convex set, and then you maximize some linear criterion over it.
But did you try some simple use to see whether that's correct?
Oh yeah, that's the point, you know.
And
If you have two states, you don't need the mediator, it's equal. We have a proof. If you have the so-called transparent motive state where the sender's payoff depends only on the action of the receiver,
Okay. Only actions of A.
yeah, U of S and A depends only on A. It's not a completely trivial case, but it's an interesting case. No need of the receiver. So, I don't want to show you this because it's too complicated. Even I get a headache reading it. This is what I said. There are so many special cases where we know that we don't need a mediator. Here is the simplest example where we think there is a gap between what the mediator can do and without the mediator, but even there I'm not exactly sure. Okay, so this is an example 3 by 3 because 2 by 2 doesn't work. 2 by 2 is very simple. So we need to go at least to 3 by 3. And the payoff of both players, they have to depend on both the state and the action. Say that these are negative payoffs. These are costs. So that the sender, he wants to be on the diagonal. He wants S to match the state. Okay, so that's the objective of the sender. And the receiver, he has a bias, a rotation bias. So he wants to match these 3 things. Okay. So there is a curve of what we know we can achieve with some condition, depending on R. And this curve here, you can see, as a function of the rate, it looks non-convex. Why is it important that this function of the rate looks non-convex? Because if it's not convex, then it means that we can somewhat convexify it. So this is high rate of communication. This is low rate of communication. So there are some sophisticated strategy where half of the time we communicate with high rate, half of the time we communicate with low rate, and in the end we get this. So again, I don't have an answer to your question, can we dispense with the mediator, or do we know that we can implement everything? I don't know. My expectation...
Explain this, I'm not sure I understand. What is R? I got it. What is receiver expected first? What is unit? So there is a randomization, and given that, what in the
So if you want, what we did here on this picture is to, so I have this convex set of things that I can implement, right? And now you said you didn't use the receiver payoff, which was correct. So let's do it now. So this convex set, let's evaluate it in some direction. So fix a receiver payoff, that gives you a direction where to evaluate it. So you calculate that, do some numerical calculus, and do some algorithm with Mathematica, and you can try to get some approximation of what you're going to get. Okay, this is what we did. And now we made the rate of transmission vary. Okay, so vary from very high to very low. And now this payoff of the receiver as a function of the rate appears to be non-convex. So why is this observation relevant? This observation is relevant because we would want, or we could develop more sophisticated strategy that would convexify with respect to the rate. And convexifying with respect to the rate means that you divide time, quote unquote time, into 2 regimes. One regime of high rate communication, one regime of low rate communication. So I don't know if this picture shows anything. That's where we are.
No, but do I understand correctly? Now, this is where the encoder or mediator can play a role. Now we have too many messages. So, with the mediator, I can convexify, right?
So,
No?
before introducing the mediator, we knew that we could get to this line here. Then we plotted this line for many, many games, and we found this example why it is not convex. And then we thought, oh, our implementation strategy was not optimal. It was not optimal because we know of a more sophisticated implementation strategy that convexifies between these 2 points.
Oh, I see. So
No, still that.
But this doesn't need mediator too.
This still does not need the mediator.
Because you can use
So
you can justify they can agree at the beginning to have high regime, low regime. Without a mediator, just let's agree that.
no, they have a, this is 0-1 page. The game with the 0-1. They cannot agree, right? So the receiver wants smaller costs and the sender higher, right? So, but do I understand correctly? So then it means that your implementation is not the optimal. There can be more sophisticated strategies that convexify.
that's right.
Convexify
That's right.
this.
The slides that I skipped are a bunch of conditions which are much more stringent than the necessary one, under which we can implement without a mediator. And where we are is to find the optimal way of implementing without a mediator. And what I'm showing you is that basically this curve is known in information theory. That's a usual strategy in information theory. And what we found with this example is that it's not optimal because of these 2 regimes that they can do without the mediator. Now, perhaps in this example, this is the best that the mediator can do. And that I don't know, that's where we are basically. But again, that's just an example to say that the problem is still complex and we are not still done with it. But as of now, our main result is that one. With the mediator, this is what we can do. And we are continuously working on getting rid of the mediator. Okay, I'll stop here.
Questions? Other questions? Olga? Yeah.
I think it's a very minor question. Do you actually use anywhere the fact that the length of the sequence is the same for the state sequence and the action sequence?
Well, the payoff are, when you calculate the average payoff, you actually do match bits, all the bits of the state sequence, you match them with the bits of the action sequence. So that's why the empirical distribution makes sense. So yes.
So it's kind of driven by application because
Yes.
Because it seems that there is a cheap generalization to it, if we see.
Such as?
Such as the n doesn't like there can be n for the s and another n for the action.
Yes. Yes, I guess you're right. I think if you look at the probabilistic method that is used in this coding theory, IID is very important. You can probably replace IID with some ergodicity property that is provided that empirical averages behave well with high probability. I think that's what's the most important.
That's for the s, though, right? This is not.
That's for the S, but then if you say that the empirical distributions are important, then it must be rationalized by payoffs which somehow depends on the empirical distribution. So if your payoffs are not fully captured by the empirical distribution, then you need to find what's the statistic, the sufficient statistic on the sequence that of states in action that actually capture the payoff you have in mind. So that's why I think there might be generalization in this direction. I agree that, but again, to make the technique work, the empirical distribution is really, really important there. So somehow, something must be a function of this empirical distribution.
And another question maybe, so can you give us some potential applications?
To OCP in particular.
Yeah. That's, so the image story. So The image story, I think it explains well where the problems come from. Now, as I said, whether it's a thing towards a concrete application to image, I don't think so. And if you talk to information scientists, they even say that their IID model is not exactly fit for I mean, these algorithms which are there, they are theoretical algorithms that prove bounds on whatever you can achieve. You cannot achieve more than that, and it's theoretically possible to achieve this and that. But then the actual algorithm that they use in image reconstruction, they are quite different. Now, when I give this talk in front of economists, I like to talk about this image reconstruction because they always think that there are too many ingredients in the model. Like you have the sequence of state, the sequence of actions. On top of that, you have the communication restrictions. And they say, well, what is the economic setting you have in mind? And plus the sender and the receiver, they are strategic and say, wow, that's a lot to swallow. But you know, my take, but it's not a concrete application, but would be think of a TikTok video. It's super strategic what you put in it. There is a huge strategy involved into what's the content of the TikTok video, yet it has to give a lot of information in 30 seconds because people don't watch more than 30 seconds. So I think there might be, you know, some rationalization of this constraint, not only by, for instance, the attention of the viewer. I don't pretend that this would be a concrete application, right? But in terms of motivation, to communicate about data which are very, very large, like videos, and at the same time having a super strategic content, makes sense. Now this is still very theoretical and very abstract from the concrete application.
Maybe one way to think about this would be saying we're dealing with a highly dimensional input and a highly dimensional output.
Yeah.
And that communication has a bounded channel is kind of natural, right?
Yes.
Kind of relative
Yes.
to this bounded channel that
Fine.
we're expanding.
Fine. Yeah. That's one of the comments that I get often is like to formulate it exactly in the way you said. Very high dimensional input, very high dimensional output, some constraint. But then why would you have a payoff criterion that would be an average? And the thing is that, again,
That's what we use in machine learning, for example. This is what we call max pooling, average of the sequences.
Mhm.
You take an image and you compress it based on a max pooling. Max pooling is a machine learning term, which means you average the content of your sequences.
Mhm.
And then what we do is your sequence here, instead of saying it's only IRD, you take it as invariant with respect to the map and equivariant to the same map. If you rotate the
Mhm,
page
mhm,
and
mhm,
translate it, it's the same thing. So maybe the problem here from high dimensional, we need to consider equivariance, invariance of, it's like doing convolutions. at some
Right,
point. So
right.
your sequence, if you change S1, S3 at the beginning and so forth, is going to say, the Kulvik label going to say, this is not the same sequence. And it works for imaging because in image we do encoder decoder. Encoder for the sender and the decode for the receiver
yes.
to understand what is the best strategy to decode it in the right way,
Mhm.
to make it statistical correct distribution,
Right.
but not far away from the message from the sender. So yet this is a pure image processing,
Mhm.
pure image reconstruction. But if
Yes.
we do generative AI, you can say this is a good statistical probability, which is I'm going to start with the image from radar, and you come to an image from me, two distributions which are statistically correct, but they're not the same.
Right.
So I think it's a good image. My problem with this is if we go high dimensional, how can we model this? That would be a good one. And this is my
Yeah. No, thank you. That's super interesting. Yeah. Yes.
Is the setup different from like credible persuasion? Because like in credible mechanism, you start from assuming that the only deviations that are possible are the ones that have the same marginals. And is this model is kind of a micro foundation for
I see what you're saying. We didn't go this way, but you see here, we stick with the Jackson and Sonnenschein approach, where somewhat they have a revelation principle in mind. That is to say, they want to incentivize truth telling. What you're suggesting would be, there are 4 possible states, and they are distributed 1/4, 1/4, 1/4. And now you demand a report of messages that would be M1 and M2 with distribution 2/3, 1/3, 2/3. And that would be a garbling of the initial distribution that would result into a Bayesian plausible distribution that you would implement. I think you could do that. I did not think of it in that way, but I think you could do that, yes.
But it also seems like
When you have the mediator, you mean?
Not necessarily. But yeah, the mediator helps, but...
No, when you say because the first set is someone who have commitment. With the mediator, you add some kind of...
Let's say that there is a mediator because it puts away the problem of encoding the reports into the message, which is a tough problem. But I think what Elena is suggesting, let's say with a mediator, is that the mediator, instead of demanding reports of states that look like the correct sequence of states, they say, just tell me messages M1 and M2, and they have to be of distribution 2/3, 1/3. What is that? This is a garbling of the truth. And the garbling of the truth, you can reformulate it into a splitting of the prior. So you could force a given splitting. So somehow, this would potentially, we need to check the details, generate the distribution that Bayesian persuasion would. But recall here that it is the receiver who has commitment power, and if you were to maximize something, you were to try to, rather to maximize the expected receiver payoff, ex ante. So I'm not exactly sure.
the end condition also looks a lot like garbling.
Yeah.
So,
Indeed.
yeah.
Indeed. But there is some kind of duality which I don't fully understand yet between distribution of states and distribution of actions. So it looks like the normal persuasion would be splitting of the prior distribution of actions, whereas here probably we can formulate that into splitting of the distribution of our actions. So maybe there is a duality between thinking of the receiver as a persuader who tries to enforce the distribution of actions. Yes, I agree with the spirit of it. I'm not exactly sure how to do that, but yes, I agree. Thank you.